we are going to discover incredible things that we never imagined.
The cosmic dawn, the first epoch of the universe, occurred roughly 100 million years after the Big Bang, when the universe was black, quiet, and empty, before the first stars were born, before the first galaxies were formed, before the first light was generated. However, what took place throughout this enigmatic time? What caused the earliest stars to form, and how did they influence the universe's development? Astronomers have spent decades attempting to find answers to some of these concerns. However, they have encountered a significant obstacle. It is quite difficult to locate the first stars. Most telescopes cannot see them because of their extremely faint light, which has been redshifted by the universe's expansion. We'll look at how James Webb Space Telescope accomplished it, what it can learn from the first stars, and the difficulties and constraints of its search in this video. The primordial gas that filled the cosmos after the Big Bang is thought to have given rise to the earliest stars. With trace amounts of lithium and other light elements, this gas was primarily composed of hydrogen and helium. As the universe expanded, the gas eventually heated up and thinned out from its initial cold and dense state. The first stars were eventually formed as certain areas of the gas became denser and collapsed due to their own gravity. Compared to the stars we see today, these stars were incredibly different. Tens to hundreds of times the mass of the Sun, they were far more massive. In addition to being thousands of times hotter than the Sun and having a significantly shorter lifespan, just a few million years, they also burst into supernovas or collapsed into black holes. The universe's subsequent evolution was significantly influenced by these stars. They created the first elements that enriched the intergalactic medium and made it possible for planets and life to emerge, including carbon, oxygen, and iron. In addition, they ionized the surrounding gas, forming hot plasma bubbles that eventually fused and reionized the entire cosmos, rendering it light transparent. Additionally, they sowed the seeds for the first galaxies to develop, which eventually grew and fused to create the massive structures we see today. However, how can we locate and examine these stars? Webb, which is intended to observe the infrared light from the early stars that is outside the range of other telescopes, can help with this. The light from first stars has been redshifted from the visible and ultraviolet to the infrared spectrum due to their extreme distance. In order to identify the first star signatures in galaxy spectra, Webb must employ a variety of strategies and tactics. These include examining the brightness variations, the intensity and shape of emission lines, and the existence of specific elements. By examining the emission lines of helium, which are the peaks of light at particular wavelengths that correlate to the energy levels of helium atoms, it may also determine the amount of helium present in galaxies' spectra. Discovering the universe's initial stars is both a scientific and a technical difficulty. Webb can test and improve theoretical models and simulations of the first stars and their creation processes, as well as get a better understanding of the early history and evolution of the universe, by viewing and analyzing the first stars. James Webb is able to learn about the earliest stars' mass, brightness, temperature, and lifetime, among other characteristics. These characteristics can help us understand how the early stars differed from the later stars and how they impacted the environment. For instance, how much energy and radiation the first stars released, how long they lived, and how they died may all be determined by their mass. How bright and visible the early stars were, as well as how they heated and ionized the intergalactic plasma, may all be determined by their luminosity. The first star's lifetime can reveal how long they impacted the early cosmos and when they gave rise to the first black holes and supernovae, while their temperature can reveal what kinds of elements they synthesized and how they enriched the intergalactic medium. Furthermore, their diversity, number, and distribution can reveal how broad and common the first stars were, as well as how they changed over time and across different regions of the cosmos. For instance, how many stars were generated and how they contributed to the reionization and chemical enrichment of the cosmos can be inferred from the numbers of the initial stars. Where and when the first stars formed, as well as how they clustered and correlated with the temperature and density of the primordial gas, may all be inferred from their dispersion. How the early stars varied in their characteristics and behaviors, as well as how they were influenced by the initial conditions and feedback effects of the primordial gas, can be inferred from their diversity. Additionally, Their relationship to later star and galaxy generations can help us understand how the early stars impacted and affected the universe's later structure and history, as well as how they relate to the observable objects we see today. For instance, the relationship between the early stars and the later stars can reveal how the former influenced the latter's formation and development by transferring their energy, radiation, and elements to them. How the first stars triggered and aided the development and growth of the early galaxies, as well as how they dictated their features and morphology, can be inferred from their relationship to the later galaxies. Furthermore, the way in which the first stars may be identified and traced using the light and signals they emit or leave behind, as well as how they can be contrasted with the objects we see today, depends on their relationship to the observable objects. In order to determine how well the theoretical models and simulations of the early stars and their creation processes match and explain the observations, Webb can also test and improve them. It can, for example, evaluate how dark matter, cooling, feedback, and metallicity affected the birth of the first stars and determine whether or not they agreed with the models and simulations' predictions. It can challenge and stimulate the creation of new models and simulations, uncover novel and surprising events, and pose fresh queries regarding the origins of stars and their place in the cosmos. It can be used to compare and contrast data from the earliest stars with data from later stars and galaxies, displaying similarities and differences as well as connections and separations. Additionally, we may combine and integrate data from the first stars with data from other sources and wavelengths to observe how they support or contradict one another and create a comprehensive and cohesive image of the early universe. Although Webb is an amazing telescope, it is not a faultless or simple task that may lead to the discovery of the universe's initial stars. Its search for the first stars may encounter numerous obstacles and constraints, including contamination from other infrared light sources. There are numerous other sources of infrared light in the universe that can obstruct or interfere with the detection of the first stars. These include the solar system's zodiacal light, the dust and gas in the interstellar and intergalactic medium, and the stars and galaxies in the foreground and background. In addition to making it more difficult to separate and identify the signal of the earliest stars, these infrared light sources can introduce noise and confusion into Webb's observations. To lessen and eliminate the contamination from additional infrared light sources, Webb will need to employ a number of strategies and tactics, including filtering, masking, subtracting, and modeling. It is not easy or clear to calibrate and understand the data that Webb will gather from the first stars. Numerous variables and uncertainties will influence it, including the sensitivity and performance of the instrument, the time and plan of observation, the processing and analysis of the data, and the theoretical presumptions and models. It might be challenging to calibrate and understand the data due to these variables and uncertainties, which can also add biases and inaccuracies. To enhance and validate the data, Webb will need to employ a number of strategies and tactics, including cross-checking, adjusting, testing, and comparing. These are only a few instances of the difficulties and constraints Webb might face in its quest to find the first stars. There are countless more that could arise and be resolved. Webb might not be able to definitively or definitely detect the first stars, and additional information and analysis might be needed to validate and improve the findings. This video has come to a close. I hope you found this video entertaining and that you gained some new and fascinating knowledge. If you did, kindly share it with your friends and family and give it a thumbs up. To ensure you don't miss any of our next videos, please hit the bell icon and subscribe if you'd want to learn more about this and other astronomy, astrophysics, and cosmology-related topics.